Welcome to the Joy of Abstraction Book Club, Chapter 23, the Yoneda lemma, one of my favorite things. It's nearly the end. This is the second to last chapter. Amazing. And we've got great questions. Thank you so much for sending in your questions. As you can see, by contrast with my previous video, it has become cold in Chicago. I'm freezing. My hands are freezing. Everything's freezing. Put the heat on. I always say in Chicago that autumn is the one day when you need neither air conditioning nor heating, and that has come and gone. So now I am afraid I've got the heat on. It was 6 degrees centigrade when I woke up this morning, so I've got my fluffy things on, fluffy slippers. Right, first question. Can we think of applying a contravariant functor like multiplying an integer by -1? I think at some level, yes, in the sense that it turns around the direction of arrows, but I don't think so in the sense that it's not an inverse to anything, and you can't really do it twice because, yeah, I don't know how far it gets us. I mean, I suppose if you had a functor from C op to D, if you then had a functor from D op to E, you can't compose those. But if you have a functor from C op to D, then that does give us, if you have a functor from C to D op, you could compose it with a functor from D op to E, and then it would be a functor from C to E. Yeah, I don't really know how far that gets us. Second question. I was beginning to get the sense that category theory was proud to move beyond sets to the point of leaving them out of the limelight. But then it looks like presheaves are bringing sets back into focus. Are presheaves a way to take all the good aspects of sets and bring them over to category theory? I mean, there's some truth to that. Category theory, it's not exactly that it's proud to move beyond sets. It's that it wants to move beyond sets because not everything is based in sets, not because you want to move beyond sets, but because you want to be able to express things categorically. You want to be able to express them in a general category so that you can immediately put them somewhere else. And presheaves, yes, they kind of are a way of taking the good aspects of sets, but not exactly to bring them into category theory, but to, as I said at the end of the chapter, to take any category C and be able to sort of embed it inside a bigger category that has all the good properties of sets. Because what we really want to do is model the good properties of sets, even in places when we're not actually in sets. How do you handwrite set? I love that question. I love these practical questions. I'd better, so to handwrite set, I would write set and underline it. I don't black or bold any of the letters. The convention is to just underline the whole thing. Is there a notion of full and faithful for natural transformations? Well, let's think about that. Full and faithful are, at some level, very set sort of concepts. Wait, I don't feel like this is necessarily in this chapter. I feel like that's for the previous chapter. But anyway, I'll answer it anyway. There was a question about limits, which was not for the right chapter. Because full and faithful is local injectivity and local surjectivity on Hom sets. And because it really is local injectivity and local surjectivity, it is very much to do with functors, and it's not extremely categorical, because injective and surjective are set things. In category theory, we would say monic and epic. So we can ask about natural transformations being monic and epic, but natural transformations don't act on Hom sets. And so I would say that it's not really a concept of full and faithful for natural transformations. So the next question is, how do we get from the definition of full for a functor to the definition of full for natural transformation? But I don't think we have a definition of full for natural transformation. I think I better just check the text to see if there's some misunderstanding happening. Hold on. Well, my best guess is that there may be some confusion about the various kinds of notation in this chapter and about which things are functors and which things are natural transformations. But everything we're talking about being full and faithful is a functor. There aren't any natural transformations we're referring to as being full and faithful. And I know it's confusing because the notation involves many things at many levels. But if you type check everything, I hope you'll see that everything that's being full and faithful is a functor. Let me just share my whiteboard screen. So in particular, this thing is a functor. That's not a natural transformation. So when we're talking about it being full, it's full as a functor. This thing is a functor. This thing is a natural transformation. Is there an intuition for why the Yoneda embedding uses contravariant and not covariant functors? It's because we're embedding ourselves into the category of presheaves, and because the category of presheaves is a good place to embed C, because it's the kind of free closure under colimits. And I'll come back to that, or maybe I'll say it right now, that someone asked what it means for it to be a closure under colimits. It is the free closure, so we're adding all colimits in. And because that's a good embedding, we can't embed C into covariant functors. So we either have to embed C op into covariant functors, or we have to embed C into contravariant functors. And so because this category of presheaves is a really good place to work, and so that that makes it more handy. So the next part of this question is there a dual to the Yoneda lemma? Yeah, I mean, in some sense, the dual to the Yoneda lemma is called density, but sometimes some people think it's just the Yoneda lemma because it's dual and it shouldn't be any different. Maybe the Australian school would refer to them both as the Yoneda lemma rather than density. So here are some specific questions. At the bottom of page 355, you say functoriality in this case comes down to associativity of composition in C. Can you think of other cases of this? Well, I have to be a bit psychic. I'm not quite sure what you mean. So it's just that because this functor is working by taking Hom sets and it's working by composition. So functoriality says if you compose on a composite, so that's kind of why it's about associativity. I don't know if there's anything much I can say about that. Next question, page 356. Can you remind me why we would be motivated to define the functor blah 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 as contravariant and not covariant? So we don't define functors to be contravariant versus covariant. They just are. We can't force something to be contravariant or covariant when it isn't. I do think, I apologize, I think there was a typo on page 356 because it says that HX sends the object X to the set AX. But HX, the correct definition is further down, is right beneath that in page 356. So HX is a functor from C op to set. And now I'm going to take this question to mean, why is it contravariant? Well, so you define it on objects. Usually once you've defined something in objects, you can tell what it's going to be on morphisms. So we define it on objects like this. It goes to the Hom set from A to X. And once you've done that, you haven't really got a choice about whether it's going to be contravariant or not, because if you start with a morphism F from A to B, you can't, if we tried over here, how could we make a function from this set to this set using a function of a morphism from A to B? Well, here, what's an element of this set? This is something from A to X. How would we produce something from B to X using a morphism from A to B? Well, what we've got is a morphism like this, there is no way to compose these to get something from B to X. We could do something more fancy, like if you had some kind of way of extending this, and there are other constructions, but if we're just going to do this by composition, there's no choice. It has to go the other way around, because if we try doing it the other way around, we can compose them. And so that's why this goes to something from C BX to C AX, because now what we're doing is we're starting with something from B to X. So this is what the result of that is. And we're sending it to, well, now we can pre-compose with F and everything will type check. So it's not that we are motivated to define it this way. It is the only way we can define this functor by composition. So if we were not trying to define it by composition, we could do something else, but we're only trying to define it by composition. So this is it just is the way it comes out. So the next question says, I need help disentangling dual categories and contravariant functors. I was under some impression that saying the functor is contravariant on this page is not necessary because we're in a dual category. I thought the direction of the morphisms gets flipped when you have a dual category, but you attribute the flipping to the contravariant functor. What am I missing? So the terminology is a bit confusing, but when you say you have a contravariant functor, you are emphasizing the fact that it is from a dual category. It is dual to the category that you would typically be thinking of. So a functor from, you cannot call it a functor from C op to set, and then you can emphasize the fact that it is contravariant. I would never write down a functor from C to set and declare it to be contravariant. I might say out loud, it's a contravariant functor on C, therefore it goes from C op to set. But I would never write it down as C to set. So I have to write down the C op, and also I say it's contravariant for emphasis. Technically, you don't need to say it's contravariant because it's just a functor from C op to set. But that's maybe a linguistic quirk or something to just emphasize the fact that it is contravariant. The next question, page 357. I'm wondering about preserving isomorphisms because the second paragraph says that HX and HX preserve isomorphisms, but I was thinking that all functors do so. Is that right? How should I be thinking about that? Yes, all functors do preserve isomorphisms. It's the very next sentence after that. It says, this is saying that the functors h upper x and h lower x preserve isomorphisms, but in fact, all functors do that, as we saw in chapter 20. And so what's going on here is that we were investigating those things preserving isomorphisms to kind of see what it meant in this particular scenario. All functors do that, so that didn't actually gain us any information. The information we gain is that that they reflect isomorphisms. So we said what we know is that if we have an isomorphism from x to y, then hx to hy must be an isomorphism. But moreover, the full and faithful part is going to tell us that if we have an isomorphism from hx to hy, it had to come from an isomorphism from x to y. Next question. Could you please say more about what you mean by canonical when you say we've produced a canonical morphism x to y from alpha? Yeah, canonical always means, or typically means, that you haven't made any random weird choices or any choices at all. That there were no choices that you could possibly make in the process of doing that, and so it was canonical. So it's like when you go to the canonical restaurant after a seminar, if there is one, it means that you always go to the same restaurant and no one's made a weird choice. Page 362, could you show how we can follow our nose in the proof of fullness? I feel like that's exactly what I did afterwards, because what we're trying to show is that H blob is full. Now, almost all of this is type checking, so it's just very important to write down carefully what you're looking at all the time. And I'm going to do it too, because when you haven't been just writing all these things out, it's very easy to get confused. So H blob goes from C to C op set. And what we're trying to do is show it's full, which means locally surjective. So we fix X and Y, and we are looking at the action on Holmes from here to the functors from HX to HY. And so we're claiming we want to show, so under this functor, F goes to HF. And we want to show that that's surjective. So we want to show that every natural transformation here is of this form, that we want to show that every natural transformation alpha from HX to HY came from one of these. That's what full means. That's what surjective means. So what does it mean to show that it's of the form HF? Well, the first thing we have to do is find an F, right? If it's going to be of the form HF, we have to find an F that it came from. We need an F. And we only have one way of finding a morphism from X to Y. So in this situation, we're given a natural transformation. So we're given a natural transformation HX to HY, right? Now, what does this information tell us? This has components. For all A, we have an alpha A from HX of A to HY of A, which means that it goes from, I feel like I'm just writing out what's in the book, but maybe it's helpful to see it live. CAX to CAY. Now we're trying to produce a morphism from X to Y. So what can we put into this situation that will produce us a morphism X to Y? Well, let's put A equals X. So in particular, we have alpha X, which goes from CXX to CXY. So this now lands in the right place to produce us a morphism from X to Y. And now, which one? Well, there's only one morphism we know exists in here, which is the identity. So wherever that goes is the only morphism we know how to produce from X to Y. And where does that go? Well, alpha X is a function from here to here. So this is called alpha X of 1X. And that's the basic Yoneda principle. This is the only thing that we know exists in this situation. And it turns out to tell us everything. So then we claim that we can reconstruct the rest of the natural transformation alpha from this, and that's what the rest of the proof is. It's just following through the definition of alpha to show that this really does give the rest of alpha. And so that's what's then on page 363. So I hope that helps a little bit. So the next question is related to this. The next question says, I'm having trouble understanding why any natural transformation H lower X must be of the form H lower F. When I try to do it, I get H upper F. Now, I think this is because something has gone wrong in your type checking. Okay, so this question has some confusion between what it says on page 363 and what it says on page 356. HF is on page 363. HF is a natural transformation from HX to HY, okay? Where F goes from X to Y. And the components of this go from HX of A to HY of A, just like that. And so that goes from CAX to CAY. So how does this work? We're starting with something from A to X, and then we're post-composing it with the thing from X to Y. Now, this is different from the thing that's on page 356. Page 356 is talking about the functor hx from C op to set. And the action on morphisms says that you take something f from A to B and you send it to something from CBx to CAX, where you take something from B to X and you pre-compose it with F. Now, it might have been more helpful if I hadn't called this F the same as that F. They're really playing different roles. However, if you start trying to distinguish everything by different letters, you run out of letters really fast. So the important thing to do is to type check everything. So this is not the natural transformation HF. This is not HF. This is the action of HX on a morphism. This is HX applied to the morphism F. So sorry about that confusion, but I hope that has cleared that up. Okay, my phone with the questions has gone to sleep. Okay. The next question, page 364. At the bottom of the page, it says the presheaf category is the closure of C under limits. I should have said it's the free closure, or the free, where you freely add all colimits. And so it is larger because the reason it's larger is that even if C has colimits, you now add them in freely. So if C already had all colimits, C offset is not the same as C. So that was a bit misleading to me. I've put a correction on the errata page about that. Page 365, could you talk more about what exactly a model of C is? Well, I don't mean a model in an informal sense. I really mean a model like when you make a model of something. So you want to take C and model it inside another category. When I said that, I was being informal to try and sum up the technical aspect of it, which is that it's an embedding. So the whole point of the Yoneda embedding is that C embeds fully and faithfully in the category of presheaves. And the full and faithful part is telling us that nothing gets collapsed or kind of expanded. So it's really like a model in the informal sense, where a model of something that doesn't collapse stuff, it just models it. So that's what I meant by that. Next question. Could you explain further how the natural transformations can be entirely determined by looking at the identity? So we've touched on that a little bit already, but I will go through it. Page 365. So this is what I said in the book, is that it's a lot like we follow a naturality square around as we did in the proof of H blob. So I would encourage you to look at the proof of H blob being full. I would encourage you to look at the proof of H blob being full and see if you can see where instead of doing a natural transformation from Hx to Hy, you replace that with a natural transformation from Hx to F. And see if you can follow it around to reconstruct the rest of the natural transformation from alpha x of 1x. So just before I do that, I'll answer the next question, because the next question says, I'm not sure I understand what this thing is. C of set Hx to F is. So this is a Hom set, right? This is the same notation as C from A to B, because this is a category and these are two objects in the category. So if we just type check this, this is a functor category. It's a category of presheaves. This is a functor and this is a functor. So this is the Hom from that functor to that functor. Therefore, it's a set of natural transformations from Hx to F. And so what we're trying to do is construct the entire natural transformation from alpha x of 1x. And I have to admit, I love doing this. It makes me a bit nervous to do it live in case I mess up some of the notation or something, but I'm just going to do it because I just love doing it. So we just have to try and remain calm, right? These are contravariant functors. So what we're looking at is a natural transformation alpha from hx to f. What's a natural transformation? It has components. So we have for all a, alpha a, which goes from hx of a to f of a. And this is c from a to x. So the Yoneda principle tells us that this entire thing is entirely determined by where the identity goes. So what that says is that for alpha, we've got alpha x, which goes from cxx to f of x. And that the only thing we know is in this Hom set is the identity on x. So wherever that goes is called alpha x of 1x, because if we carry on type checking, this is a set, that's a set, so this is a function. Functions act on elements of sets and take them to elements of the other set. So this is an element of the set f of x. So now the question is, how do we reconstruct the entire rest of the natural transformation from that single thing? Well, we use a naturality square. So the naturality for alpha says, well, the components are A, and what we have is a naturality square for every morphism from A to B. We also have to remember that these are contravariant functors, so they flip the direction of our morphisms. And what we're trying to discover is what the rest of the natural transformation looks like, which means we have to reconstruct the component alpha A, which goes from AX to F of A. So we're saying, given a morphism from A to X, where does it go in FA? So maybe I'll write that down. To reconstruct the rest of alpha, we need to say, given any A, what is the component alpha A from CAX, whoops, getting overexcited, CAX to F of X. But to do that, this is just a function, right? So we have to know where every morphism F goes. So we need to know where every F goes. So what we're going to do is use the naturality with respect to that. So we use the naturality square. Oh, I love this so much. For this F, okay? So the naturality square for this F, remember we're contravariant. So although F goes from A to X, the naturality square is going to go from X to A. So what we're going to have at the top is the component at X. What we're going to have at the bottom is the component for A. And then down the sides, we have the functors in question applied to F. So this one is the functor applied to F. So it's going to be composition with F. And it's composition on that side because when you put something in here and you've got a morphism from A to X, you have to pre-compose with F. This is F of F. See, it's flipped the direction because it's contravariant. So now what we can do, so we know this diagram has to commute. So now what we can do is chase an element around it. Which one is the color? So I'm now going to chase the element, the identity around, because the identity is the only thing we know what happens, right? Now the identity goes to alpha X of 1X here. And where it goes down here is we compose it with F and we get F. This is good, right? Because this naturality square is now going to tell us where F has to go. So F has to go to alpha A of F. And that's the entire thing we wanted to know. We wanted to know where F goes. Well, down this way, we're going to F of F applied to the element alpha X of 1X. Right, let's just type check that for a second. 1X is an element of this set. Alpha X is a function. So we do alpha X on that thing. And then F of F is another function. So we do F of F on that. And the naturality says that this has to be equal. So we can now do that on every element F and discover where it goes. And that tells us the entire natural transformation. So the entire natural transformation is determined by where the identity goes. And I just think it's fantastic. That is the general Yoneda E principle, that if you have a natural transformation from a representable to anything else, you stick in the same object, and wherever the identity goes, that determines the entire thing. It's like a kind of amazing amount of information you get from something really, really tiny. And fundamentally, I think that is perhaps my favorite thing about category theory. It's the quantity that you can know from something very, very small. And that is all the questions that we have for today. So thank you for coming this far. There's some praise and joy, praise for Joy of Abstraction, praise and joy. Thank you very much for writing the epilogue. Oh, well, that's really for next week. It put everything in perspective. I followed along with this book club, thinking I could then check the box that I'd looked into category theory. Instead of closing the book and being done, I'm now opening a door to explore more. Thank you for being the helping hand I needed to see the beauty of this subject. Maybe I'll read that again next week. Thanks, Eugenia. Thanks for a book and a book club that are helping to build up my mathematical stamina as gently as possible. Thanks to everyone for making this happen. Thank you for all your tips about doing more advanced mathematics. So many gems in this chapter. Thanks for your patience. Thanks for all your help. Thank you. This has been so much fun. It feels like I'm back in college, hopefully in a good way. This is a really interesting comment. Thank you for answering all these questions. Many of them I didn't ask because I thought I knew the answer already, but your answer is so much deeper that it widens my horizon. I'm really glad about that. The book club is a very valuable learning experience for me. And then finally, thank you for your book and the book club. Well, thank you all. It's been an epic journey. And the next one is the last chapter. So we are going to get there, and I will have to do something celebratory at the end of the next video. Thank you so much for being there. It really feels like we've come a long way. I mean, this video was very technical, so if it was a lot for you, then it is a lot. The Yoneda lemma is a lot, and so the fact that you've got to hear from nowhere is amazing. So thank you to everyone at the Topos Institute. Thank you for asking questions, everyone who asked questions, and thank you for following along, everyone who's following along. And see you next week for the last video. Bye.